This is an R2R digital analog converter, or DAC, and this is his breadboard prototype. An R2R DAC performs one simple function. It takes an 8-bit binary input and converts it into an analog voltage. The way the R2R DAC works is each bit has its own significance, ranging from 128th to 1/2, from bit 7 to bit 0. As seen in the breadboard prototype, when one of the 8 switches is opened, a 9-volt current goes through a pull-down resistor to avoid floating inputs, and then through its corresponding input on the resistor ladder. But what is a resistor ladder? The resistor ladder is what allows the digital analog conversion to take place. It functions thanks to Thevenin equivalent circuits theory and superposition theory. Using this simplified diagram, both are easily explained. To start, bits 3 through 1 will be assigned with a 0 or a low, and bit 0 will be assigned to a high. Thevenin equivalent circuits theory states that the trajectory bit 0 must travel through now boils down into Thevenin voltage and Thevenin resistance, two summaries of the trajectory the bit's current will take. Because of Thevenin's theorem, each resistor pair in the R2R DAC perfectly divides the voltage in half. Now, superposition theory. Superposition theory states that in a linear circuit with multiple sources, in this case bits 0 through 3, the total output is the sum of each individual bit's significance. One can think back to this model, which clearly shows the individual significance of each bit. This demonstration will now show the voltage output of each individual bit under a 9-volt power supply rounded to 2 decimal points. The most significant bit 7 shows half the input at 4.5 volts. Bit 6 a quarter at roughly 2.25, bit 5 at 1.1, and so on. Now all inputs will be set to high to show the max voltage that has been used during these tests. This is the same demonstration on the breadboard prototype version when being supplied with just over 5 volts. The voltage output on the breadboard prototype can be slightly inaccurate because the resistors used are ±5% tolerance rather than the ±1% tolerance used in the final device version. Thank you for watching, and I hope you learned something new. If you'd like to learn more about the CAD modeling 3D design process for the 3D printed case, more information can be found in this project design engineering report. Thank you.